I want to thank you and Carlson for the nice introduction. And also thanks for coming to the seminar. It's great to visit KTH for the first time too. This is my third time to Sweden, but the first time to KTH. All right, so in December last year, I noticed that they are like looking for distinguished lecturers. So I nominated myself. And then within one day, I got 2 reference letters. And then a few weeks later, they told me that I'm a distinguished lecturer, but I'm required to travel around the world to give lectures. And Yuan helped me coordinate this event. Okay, so this is because AESS distinguished lecturer, I have to use their format. This is their standard format. Okay.
Yeah, man, do it.
So AESS is Aerospace Electronic Systems Organization. We've been publishing papers in their journals, mostly radar signal processing papers, but they cover many topics. For AESS, they have conferences, most notably IEEE Radar Conference. That's every year. They have actually 2 journals now. It used to be IEEE Transactions on Aerospace Electronic Systems. Now they have a new one called IEEE Radar Systems. Okay, I think it just started this year. They also have distinguished lecture series, short courses. For the distinguished lectures, they have, right now, they have 38 lecturers, but covering more than 100 topics. So I'm supposed to cover 2 topics. I've been talking about this one only. The other one, I haven't prepared the slides yet. So anyways. So I'm so glad to be part of this lecture series because for this year, it's the 50th anniversary for this society. And also this year is also my 30th year at the University of Florida. So it's been a long time. Okay. Now, currently the president, Mark Davis, he's also an Ohio State graduate, alumni. And the president-elect is Sabrina Greco. She's with the University of Pisa. I visited her before. You know, University of Pisa is known for this leaning tower, right? The rumor is that if you park here, it's free. Anyways, so as I said, I've been with UF for 30 years this year, starting the 31st year. The topic of my talk today is over a century. You know, you've read the papers on array signal processing, like 2 decades of array signal. Now I want to talk about over a century of array signal processing. Okay. That's standard bio. Yuan already covered it. And this is the abstract for this talk. So let's start from over 100 years ago. In 1905, there's someone called Karl Braun. He's a German scientist. He invented something called phased array. Actually, Karl Braun, probably everybody knows about Marconi, right? Karl Braun and Marconi shared the Nobel Prize in physics in 1909. Okay. This thing here is part of his lecture series he gave. He talked about his work in 1905. Okay. So what he did was he was trying to show that he can use 3 antennas by adjusting their phases so that you can control the beam pattern where the signal is transmitted. Basically, it's just sinusoids, right? If it's narrowband, it's just sinusoids. You just adjust the phases so that the sinusoids either add together or cancel each other. Okay, that's why it's called, for narrowband array signal processing, it's called phase array, right? Because time delay means phase change. It's just sinusoids. Okay, in the good old days, when you want to show something, you have to build something, do experiment. Now we just use a computer, just laptop. So he built this thing and proved that, you know, he can control the beam patterns by control the phases. Okay, and so what he's doing exactly is this, right? You see, he's controlling basically the weight here. You have a bunch of antennas, and then you control the output, right? For him, the weights are just the phases, okay? So if you control the phases, if the W's are something like you pointing at zero direction, well, you control the W so that it points to the zero direction, zero angle. And then when you look at the response to signals from other angles, you get something called the array beam pattern, right? You're trying to point at the zero direction. You want to see what happens when you signals from other directions. And it turns out that for his standard, this Braun standard beamformer, you're going to have, for example, for a 10-element array with half wavelength spacing, you're going to have a main beam with about 10 degrees, 10 element, 10 degrees, around zero, right? And it's inversely proportional to the size. So for automotive radars, now they want 1 degree resolution. That means you have to have 100 antennas. It's too much, too expensive actually for the $150 or 300 euro automotive radar. You know, the $150 is like TM. 300 euro is like BMW. Anyways, and also another thing to notice is that if you don't control the weight, just control the phases, you're going to have side lobes. And the peak side lobe level has nothing to do with the size of the array. The peak side lobe level is about minus 13 dB. Okay, if you use weights to control the peak side lobe level, then this will be worse, right? So it comes at the cost. And also, you're going to lose SNR actually. Because when you do Windows, you're going to do it's like mismatch filtering, you lose signal to noise ratio. But those are the things we don't need to worry. So nowadays, see this here is called digital futures. Digital is the future, right? Has been around already. So nowadays, antenna outputs usually are sampled, so we are dealing with digital. So on the standard Braun beamformer, sometimes it's also called digital beamformer because you sample it and you try to do math is the same, except you are working on digital signals. Okay, so we call it this now, sometimes we call it DBF, okay, same thing. Braun beamformer, DBF, same thing. It's robust. It doesn't require anything about incoming signal. It's very robust, very, you know, this is a benchmark. For anyone doing array signal processing, delay sum, phase array is the starting point. But it has poor resolution. As I said, you know, for automotive radar, they want 1 degree resolution. With a 10 element, no, it's hard to achieve 1 degree resolution. And also, the side lobe is so high that, you know, if you have interference coming here, it can give you a huge damage, right? So interference rejection capability is bad, okay? In good old days, things don't change very fast. Nowadays, things change very fast. So from 1905 to 1969, it's more than 6 decades later, there's this person called Jack Capon. He used to work for MIT Lincoln Labs. Okay, we couldn't find a better photo of him. that's him. Okay, he published a seminal paper in 1969. This is the first time we started something called adaptive arrays. That is, we control the weights based on the data. So it's data adaptive, not data independent. So Karl Braun is data independent. Here we're talking about data adaptive array signal processing, right? So, so in 1960, there's something called a minimum power distortionless response. We usually call it Capon beamformer. Okay. So this started this adaptive array signal processing era, and it's continuing even today. Probably in the next, I don't know, 10 years, there will be still more and more papers published on this topic. Okay. Every year, a new paper is coming out, still focusing on this topic. So the idea of this Capon beamformer is this. I want to minimize the array output power subject to the constraint that I want the signal from this direction coming through undistorted, right? And the trouble is you need this. That's ensemble average of the array output. It's ensemble average array covariance matrix. In practice, we don't have this. That's the trouble. But anyway, this math is simple, right? Cauchy-Schwarz inequality, you can get this weight and you can get this power. The trouble is, you don't have snapshots in a lot of applications. You talk about automotive radar, the latency is very short. You're collecting your snapshots, you're already hitting somebody. So that's the trouble, okay? In a lot of applications, we only have a single snapshot. Okay, you can say, oh, I have a huge array, I'm gonna do spatial smoothing, cut a big array into subarrays to create snapshots, but then you are reducing the aperture hugely, significantly to start with. You're sacrificing a lot to get some snapshots. So here's the trouble. How do you get a good, decent R hat? That's been a struggle since 1969 for array for adaptive array signal processing people. Okay, so later on, like music, spray, and all these things, they also depend on this R hat. Okay, but in practice, a lot of times we only have one snapshot. Sometimes we have a sparse array. You can't do spatial smoothing if you want to do. Okay. It turns out that this is an interesting connection. There's someone called Harry Markowitz. He got a Nobel Prize in economics in 1990. In 1955, that's before 1969, right? In 1965, he wrote a paper called called portfolio management theory to reduce risk optimization, right, for some kind of expected return. Turns out that this is the first revolution in Wall Street. And also, the theory is still the foundation to modern day investment strategy. The economics papers sometimes can be very mathematical, right? So if you take out some of the constraints, and then you get exactly the same problem as Capon. So this Capon beamformer problems has been studied as special cases by Markowitz. Okay, so that's an interesting connection, right? But anyway, so as soon as Capon published that paper, also from MIT Lincoln Labs, especially in the good old days, in Lincoln Labs, statute is very high, right? So it gets a lot of attention. People want to use it in practice. But the problem is, in practice, Capon is sometimes disastrous. Why? Because it has a tendency to suppress the signal of interest. Meaning, if you're not careful when you use Capon, you can suppress your signal of interest. So if you do that, then the performance is worse than Braun's method, right? So in practice, few snapshots are available in this paper by Asa Bagara and Harry Cox. They talk about in their applications, they have 3 snapshots at most. Okay, we are all humans. We can never calibrate the array to be perfect. There will be always calibration errors. Signals are correlated or even coherent. I have to talk about coprimary. You heard about that lately, coprimary in recent years. The so-called coprimary in that topic, they said, oh, I can use M+N antennas to achieve some kind of aperture, it's M times N. But one of the fatal assumptions is this: all of the incident signals must be completely uncorrelated. Almost like you are playing God, saying, hey, all of your incoming signals, you must come to me completely uncorrelated so that the matrix is diagonal. You don't have that in practice, right? So that is a very strong, restrictive assumption. But anyway, so in practice, sonar, radar, whatever, you always have multipath. You always have something like in communication, right? Multipath, something coherent, correlated, or coherent, or whatever. Okay. And also for sparse arrays, spatial smoothing is not possible. And also spatial smoothing itself is kind of, you reduce a big array to like much smaller, right, to create some snapshots. That's not an optimal thing to do, actually. But anyway, still people try to say, to use this to replace that in practice. So then the question is, if all the conditions are okay, it's great. So data adaptive is suppress interference really well, give you high resolution, everything. Except when you're using it in practice, it suppresses your signal of interest. It's worse than Braun's beamformer. So then since the publication of Capon beamformer, a lot of people, I think, I don't know, thousands, tens of thousands of papers have been written on robust Capon beamforming. Okay. And one of my beamforming heroes is Harry Cox. Okay. Member of the Academy of Engineers, US. He's with Lockheed Martin. He's the first one to make Capon work. Okay. So you see, 1973. So the other day I was talking to him, he's like, oh, who's counting? I've been at this for half a century, right? From this paper till now, it's half a century. He's still working on this. He's still, as of today, working on this, okay? Now, let's see how he dealt with the problem. Here's the thing, suppose that your signal is from A0, the steering vector A0, and you'll assume, you don't know, right? So your assumed steering vector is from A, for example. And then remember, your goal is to minimize the array output power. So then the W will try to be orthogonal to that because, W knows, right? Because the R or whatever R hat you're using tells you about it. You're trying to get rid of it. So W and then A0 should be orthogonal to each other to satisfy to optimize the fact that you want to minimize the array output power, right? And subject to the constraint that the signal from, because that's what you don't know, so you assume, right? This guy needs to come through undistorted. Now, because they're close to each other usually, this angle is almost 90 degrees. So when W was trying to get rid of A0, W needs to be long, right? In order to satisfy this constraint. This is almost 90 degrees, so W needs to be long to satisfy this constraint. When W is really long, this norm is long, that means the noise power is magnifying noise power. Your signal is gone. Remember signal suppression? That's the fatal flaw of Capon. Signal is gone, but your noise is magnified. You don't have a signal anymore. Okay, whatever you see is noise amplified. That's a key, right? So he observed this, he proposed something like this. Don't want W to be too big. So I constrain the W to make the Capon beamformer more robust. Okay, so this thing, even today, I'm sure in some practical systems, people are still using this. This is the first time to make adaptive array work for practical systems, which is why he's a Academy of US Academy of Engineering member. Okay, so when you solve this problem, you see the same thing, right? Minimize array output power, signal undistorted, and then W cannot be too big. And then the solution is something called diagonal loading. You add a diagonal to your R. Okay, you add a diagonal to your R. And this diagonal loading is very interesting. When gamma is 0, you go to the standard Capon. When gamma is infinity, because then this R doesn't matter anymore, right? It's just the Braun's beamformer. So gamma connects Braun's beamformer from 1905 to the standard Capon beamformer in 1969. Okay, so in practice, to make it work, it's somewhere in between. But picking the right gamma itself is an art. You have to try. People say, oh, I'm going to make gamma the noise power. And then that means you have to measure the noise power. Okay, but anyway, it's a user parameter, right? So this started this era of robust Capon beamforming research. And I still see tens of, papers published every year now on that topic. Today, this year, maybe next year, I don't know for the years to come. So you see, that's the problem, right? How do you determine delta nicely? You don't know, right? And also, those are the papers, right? The robust that beamformer, they still they are still in this Capon box. I still need R hat, right? They're still in that Capon box. So then if you have single snapshot, what happens? Your R hat is so bad that you pick a huge gamma for it to work, which means just keep Braun beamformer, right? So for single snapshot case, for highly correlated coherent case, whatever, this thing doesn't work. Or it degenerates back to Capon beamformer. That's a trouble. So I want to mention a guy, he legendary Irvin Reed. For communications people, you heard about Reed Solomon code, right? That's a guy, okay? He's legendary. And he once upon a time worked for MIT Lincoln Lab. So this is a seminal paper. Everybody cites it, okay? But for this paper, he was talking about space-time adaptive processing for wide area surveillance radar, okay? So for his problem, it's like you have a range bin. You want to know if there's a moving target. You use adjacent range bins to get you something called Q hat, because that target is not in your adjacent range bins. So this guy here does not have a signal. It has only noise interference. These guys has noise interference. Okay, so when you don't have your signal of interest in this thing here, that's called a minimum variance distortionless response, whatever. He did this analysis here and says that if my number of snapshots is 2 times of the dimension, my performance loss is 3 dB. But that's for the case where you have Q hat, no noise in, you have no signal in this. Your signal cannot be in this. For his rule of thumb conclusion to be valid. Okay, your number of snapshots needs to be 2 times the dimension, but it's restrictive. It's not general array signal processing. It's for the case where you don't have signal in your data to get this so-called covariance sample covariance, noise and interference sample covariance matrix. So we did some. We wrote some papers and published an edited book on this topic too. Okay, for all of this here and here, we are also still in that Capon box. Okay, but as long as you are in the Capon box, you're in trouble when there's only a single snapshot, when you have highly correlated or coherent signals. And also user parameter, you don't want user parameters in practice. I mean, you don't have a luxury to adjust around, right? In a lot of applications. So here's an example of this Capon family of array signal processing, adaptive arrays. See, when you have 2 signals that are coherent with each other, say, this is a signal, that's a signal. They have the same temporal signal, the same signal from 2 different directions. What happens is you can write that into this. You get a steering vector. That's not equal to any of this. You cannot find a theta so that this plus this is equal to this, right? And you don't know what that is because there could be scaling or whatever, right? So you don't know. You never know how this is combined. There could be scaling on both of them. Then what happens is when you scan around theta, what happens is everywhere, say you have 2 coherent signals, right, from these 2 directions, everywhere they're suppressed. Okay. This is a Braun beamformer. That's where the true powers are. Because of the resolution problem, you know, it's 2 are added together. But this Capon performance here, everywhere the 2 signals were suppressed. The fact that you have a bump here is because the noise power is magnified. You know, when you're pointing here, right, you're trying to suppress the signals, the noise power goes up. Okay, so you've already, you know, this looks nice, right? There's a bump, but you lost all your signals. It's just noise left. Okay. All right. So actually, I was traveling in Scandinavia that year. I think 2008. Second time I was in Sweden. We went to Finland, Estonia, Denmark, Sweden, Denmark, and Norway that summer. Actually, I came up with this idea and I gave it to a student. They tried it, it worked really well. This is something called the iterative adaptive approach. Okay, it's trying to jump out of this Capon box so that it works for a single snapshot, it works for arbitrary arrays. Okay, so so you see, overcome the limitations through this. That's the keyword, iterative. I'm going to talk about that. And it has all the nice things about Capon beamformer, high resolution, interference suppression capability, and all that. But it doesn't have the problems of Capon. Okay. And I'm going to show you, AI has been used widely in practical applications. I'm going to talk about Intel patent on this. We've written a bunch of papers. So, you know, AESS is very slow in publishing papers. You know, from to appear sometimes takes 2 years. But anyway, the paper published in 2010. And then we were working, right? That's why you have more papers. It's because it takes so long to appear. Jian also worked on this IA fast implementation thing, right? Fast implementation because the topless matrix, you're trying to utilize that to speed up the computation. Anyways, so let's see how IA jumps out of this Capon framework. So you take your angle, say from -90 to 90 degrees, you put them into grid. Usually the grid size is 5 to 10 times finer than the Rayleigh resolution. Why? Because it's super resolution algorithm. Okay, too fine is not needed because actually, you know, if you want your method to work in practical data, resolution improvement by a factor of 2 is plenty good. When you want 4 times or whatever resolution improvement, sometimes you rely too much on the parametric model. So that when you rely too much on the parametric model, your algorithm becomes too sensitive, meaning it requires higher signal-to-noise ratio, more accurate models. You know, some people tell me that, you know, somebody was trying to sell them some algorithms, saying, hey, it has really super resolution. And then they use the measured data to show that. But it turns out the measured data is in an anechoic chamber with 2 ideal point, like corner reflectors. So it's like a pretty pure sinusoid with pretty high SNR. Then you use all kinds of methods, right? But in general, when you drive on the road, you don't have that luxury. You don't have all the high SNR scatterers for you to enjoy, right? Anyways, so again, 5 to 10 times is enough. And then you would break that into grid points, right? And then we write the data in this way. We have signals from all these, we have signals from all of these angles. They all have some kind of thing, signal with it, and the noise. And then the array steering vector, then because this is 10 times, 5 to 10 times more than the resolution, Rayleigh resolution limit. This A matrix is a fat matrix, meaning 5 to 10 times fatter than the top highness. And then we assume because when you have a single snapshot, the incoming signal being coherent or not is irrelevant. Remember, incoming signal coherent or not is a temporal property, right? When you have a single snapshot, there's no, it's coherent, uncorrelated, it's not an issue. Okay, so we just assume diagonal. That's where we get toplets matrix, right? Vandermonde, diagonal Vandermonde. It's a toplets matrix. Anyways, so we got this covariance matrix that's different from the sample covariance matrix. That's not from the data. It's a fictitious covariance matrix. I just say, you know, I have the signals at all these grid points. They all have some kind of power of signal. This is a complex value. So we keep the phase, we keep the amplitude. Okay. And then you know, you're going to say, well, you don't know this. We don't know this. So we do iteration. And you remember, I'm a fan of Braun. DBF is robust, right? If you're a fan of Braun, you still start with Braun. You start with one dBF, okay? You get a rough idea of what that is. You build that, and then you update it and do it again, like 10 iterations. Voila. You get a pretty nice result. So that's where iterative adaptive approach comes from. Okay, the key is we jump out of this covariance matrix thing. We use fictitious, and then we don't know a lot of things in it, right? We don't know this guy, so we do it through iteration. Okay, and then the guy tried it. It works very well. Actually, there's a guy who got his PhD from Uppsala University, and he got a job with University of Newcastle in Australia. He said he tried IA for all the data he can put his hands on. I never disappointed him. Anyways. Okay, so you see, how does it work? Suppose I have ideal Capon beamformer, meaning I give the condition that's ideal for Capon. Infinite snapshot, uncorrelated signals, no array calibration error. So condition is perfect for Capon, right? This black curve is Capon. Okay, suppose I have two signals coming from here. And then this red curve is the single snapshot IA. So you see high resolution properties and also suppressing the side lobe to almost noise level. You see this noise level, right? Because SNR 20 dB, you have 10 antennas, so it's a 30 dB gain. So you see if your signal is 0 dB, then it's minus 30. That's the noise level. So you see single snapshot IA basically suppress the side lobe level, this red curve, to basically the noise level. So IA has a super resolution capability, usually by a factor of 2, and it has excellent super side lobe suppression capability to the point that you can suppress the side lobe to the level of noise. Okay. Now let's see how it works, like in the iteration of the movie. So I have two signals close to each other. It's a sparse array, so you can't do spatial smoothing, nothing. So I have two signals. You see this now. The iteration, the starting initialization is the Braun's dBF. Look at each iteration. 10 iterations. See how it goes. See the side lobe level. You have a sparse array, so you have a very high side lobe level, and the resolution is dBF is, you see here, sparse array, high side lobe level, resolution not great. And then through iterations, you suppress the side lobe level, you get super resolution. One, 2, 3, 4, 5, 6, 7, 8. You see the side lobe level is really reduced, right? We've collaborated with a lot of papers with Professor Stoica. As you can see, his name is everywhere. So he published a paper. We published a paper with him together. He's the main author on this. This is a very interesting paper. This one here, weighted spice, a unifying approach. It turns out that under this umbrella of weighted spice, we have all these algorithms included as special cases, depending on how you adjust the weights. You have IA, spice, slim, likes. All of these are iterative adaptive approaches. Another good thing, all of these are hyperparameter free. You don't need to adjust the user parameter. Okay, not like a robust Capon, you have to know the diagonal loading level, whatever. No. And it turned out that, Dave Zakaria, he tried on a lot of numerical cases. It turned out that I is the most robust, most likely the most robust among all these family of algorithms. Slim, for example, may have better resolution, but needs higher SNR. Right, its convergence is a little shaky sometimes when you use it for practice. Anyways, and let's talk about the applications for IA. recently, the Vincent Poole, I think communication people know him very well, right? He's actually a US Academy of Science and Engineering member. And he co-authored a paper recently on radar. Okay. Actually, this guy, he got his PhD from Rutgers University, Sun Chao-sun, and he worked for Delphi for 3 years on angle estimation. Delphi, I think Bosch is #1, Delphi is #2 automotive radar company in the world. The #1 in the US. So Bosch is German, right? Delphi, and then Continental is German. Delphi is now called Active. Okay, so he worked 3 years for that company on angle estimation. Remember I was telling you that automotive radar, they want one degree resolution, but they are not willing to pay. Because automotive radar cannot make it too expensive, right? So basically then this paper is practically relevant because he's 3 years of practical experience, right? In the automotive radar company. Okay, so in this paper, he compared a bunch of algorithms. One of them is IA, okay? Now, also I want to tell you that attaining this 1 degree of azimuth resolution is still a challenge. Given the cost, how much money you are willing to pay, achieving that is still not, it's still a goal. Okay? Still not realized. Anyway, so this is a table from their paper. This is from their paper, okay? Let's see, DBF, that's Braun's method from 1905. Music is pretty, probably if you've taken any classes, you know this textbook stuff, right? Subspace-based methods. OMP, orthogonal matching pursuit. Actually, it's just a small change from matching pursuit, right? But matching pursuit is related to clean. Clean was published in 1974 in the Astrophysics Journal. So it's reinvented, okay. But for all compressive sensing algorithms, he used only OMP and IA. Okay, so see here, robustness. Only these 2 guys earned the strong robustness thing, property. The others are all medium. Okay. And had high resolution. Usually the resolution compared to that is a factor of 2. And the side lobe level capability, this is much, much higher, suppressing the side lobe to the noise level. Okay. So here's an example. This is a distributed signal. Like it's a rectangular pulse, basically. The true spectrum is like spatial spectrum is a rectangular pulse, like distributed target, whatever. DBF, robust, of course, right? No problems, even when your spectrum is just rectangular pulse. Okay. So compared to Braun's DBF, side lobe level, low, really low to the noise level. Here's an example of 2 signals. Oh, by the way, in automotive radar, you also have dynamic range problem. Okay, you have the return from the semi truck. It's going to be much, much stronger, more stronger than a cat, than a fuzzy cat, right? So 60 dB stronger easily, yeah. So for this case, the DBF will, because the side lobe, it will bury this lobe. It's not visible at all, right? In this black curve, you don't see that second target. But this is IA, the red curve. You see the super resolution thing, and then suppressing the side lobe so that this guy here is reviewed clearly. So that's what this is. Side lobe level much lower. Weak target is exposed, and interference. As far as this guy is concerned, that's interference, right? So interference rejection capability is much stronger. All right, let's talk about the subspace-based methods. Okay, they are parametric methods. By the way, I is non-parametric. Okay, parametric methods need a parametric model. You need the user parameters, the number of signals, right? Subspace dimension. Signals cannot be correlated, R hat, all those problems. So even for the uniform linear array, you do spatial smoothing. We'll see. We'll see how it works. Okay. So compared to that, usually it works well for single snapshot array. They don't work. Music in the spray do not work when you have a single snapshot sparse array. They are not user parameter free, actually. You need a number of signals. Okay. Let's see how it works for this. That's what you get for music. For that pose. So for parametric methods, you need the signal model. You need a noise distribution. But for the non-parametric IA, you don't need any of that, which is where the robustness comes from. Now you're going to ask me, why doesn't IA have the signal suppression problem that Capon has? That's because even my steering vector is wrong. The fictitious R, that A and the A outside, they match. That's why you don't have a signal suppression problem. Remember the R1 is from sample covariance matrix from your data. The signal, the steering vector in that can be different from what you assume. But everything is assumed. So you don't have the signal suppression, the fatal problem of standard Capon. Okay. Anyways, that's music and the spray. And compressive sensing methods. OMP, as I said, it's a simple change of MP, which is clean, basically. Probably clean is better. Because you allow for clean, you allow the signals to be not on the grid. Okay. Anyway, compared to that, it's also doesn't have user parameter, for OMP, when do you stop? So that's how you have OMP, orthogonal matching pursuit compared to IA. No user parameter, right? This one you don't know when to stop. More robust, okay? And also, OMP probably want a sparse spectra. You don't have to for IA. And actually, the paper said, oh, IA has a drawback. It needs the signal to be on the grid. No, that's not true. Remember when we divide the angle into grid? But your signal does not have to be on the grid at all. But you need to have a fine grid, because it's a super resolution method. Okay. So for general, like lasso, square root lasso, those are the compressive sensing methods, right? They all have a user parameter. Like the lambda in lasso and square root lasso, it's hard to choose for practical applications. Here, not needed. Sparsity, not needed. Usually they need this, right? L1 norm to enforce sparsity, whatever. And obviously, people in industry discover that IA is really robust. So there's this US patent, 2020, Intel Corporation, somewhere, where? I know it's here, yeah? Intel Corporation. Actually, it's a Mobileye. Mobileye was purchased by Intel, so these people are all Mobileye people. Okay, they filed a patent called beamforming techniques implementing the IA. Okay, so they came up with two approaches to speed up the computation, basically. All right, one is RCI doesn't work very well, and the other one is this. I want to reduce computation, right? So what I can do is I can use Braun's method to go to the spectrum, and for the area of interest, I cut it out, back out to here, and then apply. That's the idea. We use it all the time. I don't know why they patented it. So they patented two ideas. One doesn't work very well. Actually, you know what motivated me to nominate myself for this distinguished lecturer? Actually, this is the first time, I mean, I'm doing this, giving talks everywhere in my life. It's this patent. So one doesn't work very well. The other one, we use it all the time, but they patented it. Another thing is, in the whole patent, they did not mention any of our work. You can dig it out, it's all online. No mention of our work at all. So I asked Yuan, what am I going to do? Yuan, I don't know. So I decided to give this talk. Actually, it was like a spontaneous kind of thing. I nominated myself. It was due right away, but I got 2 letters. One from actually Petri within 1 day, right? You need a reference letter to be a distinguished lecturer, and then the other one is from Rick Braun. They were like fast. They were faster than me. They gave me a letter within 1 day. So it's I didn't plan this, but it's working out, and I get to spend a month at KTH. That's wonderful too. Another thing that's interesting too. See, look at this date. Last year, it's within 1 year, right? DARPA started something called the BLIP program. I hope it's not BLIP. I hope it's going to be longer than that. But anyway, started something called BLIP program, which stands for Beyond Linear Processing. Okay, let's take a look at their goal. It's directed towards general needs, radar signal processing, right? With a view to demonstrate feasibility and the practicality of nonlinear and iterative signal processing. So when DARPA starts a BLIP program, there's general moolah. Oh, my kids, I like to say moolah. Money. I don't know, in Swedish, money means what? How do you say money in Swedish?
Pengar.
Huh?
Pengar.
There's money associated with that, right? Hopefully with the support of the money, this area can really make a lot of progress. Okay. I think that's all I have. I don't know. Am I too fast, too slow? I don't know.
Yeah.